All right, so we have to be able to predict the product. We have to be able to predict the reactant. We have to be able to predict what reagent would be used in different reactions. And also, we have to be able to draw the mechanism itself. Mechanisms will help us to understand what the product would be so we don't have to predict it in the future if we can just understand the mechanism. So really the mechanisms are how we should be predicting the product or the starting material or the reagents. By knowing the mechanism, we can kind of figure out any piece of it. So what would the mechanism be for this? Well, we have a tertiary alkyl halide that can only do unimolecular things as far as substitution because it's blocked. Also, we have a weak nucleophile. So both of these things are saying it must be an SN1 mechanism because weak nucleophiles wait around. What do we have over here? We have H3O plus and Cl minus. We have to somehow form those in the reaction because they're listed as products, and we're substituting an OH onto our ring. So pause the video right now and try to do this yourself. You should be able to do this at this point. All right, you're back. Good to see you. All right, so this is an SN1 mechanism. That means that it's the rate determining step is the dissociation, the leaving of our leaving group, Cl minus. When that occurs, we would have a carbocation. What else is in solution is water. That's our solvent, and Cl minus. The water would then, the oxygen is partially negatively charged, and that partial negative, is drawn to the positive charge on that carbocation. That would then generate the oxygen carbon bond, but we still have 2 protons on that oxygen atom. So we have to somehow pull this hydrogen off. And what's going to do that? What's going to pull that hydrogen off? To figure that out, we just got to look at the products. And also we can do it from a variety of ways. If we look at the products, we know it has to be water, right? Because we're generating H3O plus somehow. So we can do that by just pulling it off with water. Also, let's think about the nucleophilicity of H2O versus Cl minus. So what's a stronger nucleophile, Cl minus or H2O? And to figure that out, we have to think about the conjugate acids of those. The conjugate acid of Cl minus is HCl. This would be H3O plus. So which is a stronger acid? We have 2 pKa's for each of these, or 1 pKa each. So pause it. What's the pKa? What's the pKa there? Good job. -7. What's the pKa here? Good job. -1.7. So when it comes to why is water deprotonating that versus why didn't chlorine deprotonate that, it's because water is a stronger base, and we can say that definitively because we know the pKa's of those two things. So great job on that. There's another one on the page, so try the one underneath and then turn the video back on. All right, you're back for the second mechanism. Exciting times. So, looking at this mechanism, what are the clues? Is this going to be an SN1 reaction or an SN2 reaction? So, we have multiple clues here. A secondary alkyl halide. What does that mean? That means it can be either SN1 or SN2, right? So that doesn't really help too much. What about our nucleophile? What was our nucleophile? Somehow an oxygen is there attached to that spot. So where could that have come from? I guess it must have come from the oxygen also attached to the molecule. How can we figure that out even more? Let's number the carbons. 1, 2, 3, 4, 5, 6, 7. So if we number the carbons, we should have 7 carbons over here as well. 1, 2, 3, 4, 5, 6, 7. So we have 7 carbons, and carbon 3 is where the leaving group is, and that's where the oxygen is substituted. So it must be this oxygen that is the nucleophile. Okay, so that's another clue. There's our nucleophile. As it's drawn, does this nucleophile look strong or weak? Okay, you answered. It looks weak, right? It's neutral. But this has to be an SN2 reaction. How do we know that it's an SN2 reaction? Think about that for a second. The product, right? What about the product tells us that it's an SN2 reaction? The stereochemistry changed. So this is just a dash here, and it was a wedge there. So this has to be an SN2 reaction. Okay, we know it's an SN2 reaction, but this is a weak nucleophile. So how is it going to become a strong nucleophile? Because strong nucleophiles are what does SN2 reactions. And if we think about it, let's look what we have on both sides. We have this thing that has 2 negative charges here. What is it over here? Oh, one of them has an H on it. So it looks like this acted as a base. It accepted a proton. So it probably accepted that proton from that OH. So looking at that acid-base transfer, that would provide the alkoxide here. And now we have our strong nucleophile. We have our strong nucleophile, and also this arrow, I'm not even going to draw the product of it because it's already over there. We added a hydrogen to one of these oxygens. And where did that come from? That came from the lone pairs, not just the negative charge, because it's electrons that move like that. All right, what's the next step? Well, we have a strong nucleophile. We have a secondary leaving group. So this is just going to be an SN2-like reaction where that will add to that position and knock off that bromine. And that's it. It looked a little bit complicated, right? It looked complicated when we made this ring thing. We had an acid-base reaction that happened first. Those were things that are kind of new to you. But I think that by looking at what the starting materials are, what the products are, that would allow you to solve this problem. So, good job working on it, and I'll see you on another time.